Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X published on November 6, 2025, about 3 days ago. This paper shows that a photorealistic simulator built by combining 3D Gaussian splatting with physics-informed soft-body digital twins can predict real robot performance with strong agreement, achieving Pearson R greater than 0.9 across tasks, for example about 0.94 on toy packing, about 0.90 on rope routing, and about 0.92 on push T. The paper is titled Real-to-Sim Robot Policy Evaluation with Gaussian Splatting Simulation of Soft Body Interactions. And as we'll see later, the implications for scalable, reproducible policy evaluation are significant. Also, the authors shared the official repository for the framework. Inside, you will find the simulation engine with Gaussian splatting, Hydra configs, a policy training submodule, evaluation scripts with multi-GPU support, keyboard teleoperation and motion replay, clear UV and CUDA setup steps, downloadable assets and checkpoints, and utilities for rollout visualization and success rate computation. Alright, the repository details were clear. Figure 1 presents the headline result. Simulated success rates closely track real success rates because the points cluster along the diagonal trend. The left panel plots simulated versus real success rates, with colored markers for ACT, diffusion policy, pi 0, and SMOL versus LA. The image panels on the right show simulation on top and real executions below across 3 tasks: toy packing, rope routing, and T-block pushing. The consistent motions and outcomes illustrate why the correlation is high. While Figure 1 showed the headline correlation, Figure 2 presents the full pipeline, which turns real demonstrations and a phone scan into a simulator that evaluates the same policies. The left side illustrates policy training from real data and motivates sim evaluation because it is cheaper and scalable. The right side depicts reconstruction with 3D Gaussian splatting, positional and color alignment, and phys-twin optimization, so deformable objects move realistically. The bottom row shows the constructed environment exposing step and render calls. Okay, Figure 3 shows simulated success on the vertical axis versus real success on the horizontal axis across tasks and policies. The 3 left panels hug the diagonal, with correlations around 0.94 for toy packing, 0.90 for rope routing, and about 0.92 for push T. Error bars reflect Klopper-Pearson uncertainty from finite trials. The right panel contrasts Isaac Lab, which scatters widely with R near 0.27, against the tighter high-slope cluster from this simulator. So the previous figure contrasted overall correlations. Figure 4 shows per policy, per task learning curves, with blue for simulation and orange for real rollouts, so the trajectories can be compared across training. The trends generally track, which means checkpoint rankings and simulation match reality. The toy packing diffusion policy panel peaks near 5,000 iterations for both curves. The rope routing pi 0 panel crests around 20,000, with simulations slightly above real but following the same shape. Alright, the previous figure tracked learning over time. Figure 5 compares visual rollouts across 5 columns, so rendering and dynamics differences are obvious at a glance. The left column shows real-world executions. The second column shows our simulator, which matches poses and outcomes closely. The middle columns highlight failures. Without physics optimization, the rope misses the clip, and the plush limbs misfit, while without color alignment, the robot pushes the T-block differently because perception shifts. The rightmost column shows Isaac Lab with noticeably lower realism. So the previous figure highlighted qualitative gaps. Table I reports the quantitative story. The full simulator reaches R about 0.94 on toy packing, about 0.90 on rope routing, and about 0.92 on push T, with mean maximum rank variation near 0.09, 0.10, and effectively 0. Removing color alignment or physics optimization lowers correlation and raises ranking errors. Isaac Lab trails, with R about 0.24 on rope routing and about 0.65 on push T. Wrapping up, 2 takeaways stand out. Photorealistic 3D Gaussian splatting combined with physics-informed soft body twins predicts real robot success with around 90+% correlation, and both color alignment and physics optimization are required for that reliability. The broader implication is scalable, reproducible policy evaluation that cuts lab time and accelerates safe iteration. Thanks for listening. I am Alex, signing off.